Okay, the last speaker this afternoon will be Jørgen Rennemo. He will speak on the homology of Hilbert schemes of a locally planar curve.
Right. Yeah, so first of all, I'd like to thank the organizers for giving me the opportunity to speak here. And yeah, so the title of this talk is the homology of Hilbert schemes of a locally planar curve. So we begin by fixing a algebraic curve C over the complex numbers. And we want this curve to be proper, reduced, and irreducible. And as the title indicates, we want this curve to have locally planar singularities. So locally planar singularities means you can say that analytically locally at each point you can embed your curve in the plane, or alternatively you can just say that the dimension of the cotangent space at each point as a vector space, this is less than or equal to 2. So yeah, this holds for all points of the curve. And yes, we will be studying the Hilbert schemes of points on this curve, which we denote C bracket n. And we will in particular be looking at the topology of this space. So naturally this depends on the topology of C. So if you just start by looking at the very simplest case when C is actually smooth, then let's see. So if C is actually smooth, then this Hilbert scheme is just the n-symmetric product, just the n-symmetric product of C itself. So so points of C are then just points of Cn are then just collections of points of C with weights attached to them. So if we then want to look at the homology of this thing, then that's fairly easy to describe. I should probably say something about the choice of coefficients here. So I'll be doing homology with rational coefficients throughout this talk. So it might be that some of these results actually can be given in more, can be given a stronger form with integral coefficients, but for simplicity we just stick to rational coefficients here. And in particular that means that I will sometimes just switch between homology and homology, because in certain ways of phrasing this, homology is natural. It's a natural thing to look at, and in other ways, the homology is more natural. Well, anyway, so this thing is then the homology of Cn. We'll take the Sn invariance in this space, and this you can write as. You can give a formula for this in the following way. Take the symmetric powers of the even part of the homology, and you wedge with the antisymmetric, or the wedge product of the odd part of the homology. Okay, and then of course here the odd part is just H1, and the even part is just H0 and H2. So, moving on to the more interesting case of where C is actually singular, then the Hilbert scheme will be parameterizing subschemes, and these can be described by, you can split the support up into various points, and then at the non-singular points you just specify their multiplicity, and at the singular point something more interesting happens where you have to specify a subscheme structure. So in particular then, the topology of the Hilbert scheme depends on the singularities. So as we've seen today, you can use that to define, you can use this to define enumerative invariance and to study, to actually count curves having specified singularities. You can also use this to define invariance of singularities and study the singularities themselves through this, through studying the topology of Cn. But what we're going to do today is just restricting to the problem of trying to understand the homology of this Hilbert scheme. And trying to get something which is similar to this. So one of the goals is to get a formula which is somewhat similar to the thing you have in the smooth case. Of course, not nearly as explicit, but still reminiscent of this. So, in order to describe the answer, we need to introduce the compactified Jacobian. Which is to be precise, I mean here. So J is the scheme parameterizing coherent sheaves which are rank 1, total free, and degree 0 on C. So line bundles are, of course, examples of points in this. So this space is proper, and therefore it is a compactification of the Jacobian. And so when C is singular, if you just take the Picard scheme, then this thing will be, the Picard scheme will be non-compact. So this thing is then a compactification of that. And when C is locally planar, it's actually a very nice compactification. It has, so let me just write down some properties of this. The Picard scheme sits inside J as an open dense subset. So there are no extra components appearing here. And also J is proper, reduced, irreducible, and has LCI singularities. So this is due to Altman, Kleiman, and Yorobino. So J is a very well-behaved complication of this Picard variety in this case. I should also say that when C is locally planar, the same good properties hold. So these being reducible and LCI also hold for the Hilbert schemes. So these are then related by the Albert-Jacobi map, which we've seen some variants of already today, which basically just comes out of the fact that if given a zero-dimensional subscheme of your curve, you naturally get a maximum total free sheaf by just taking its ideal sheaf. So you've got this Albert-Jacobi map going from Cn to J, sending a subscheme to the ideal sheaf set, and then you have to twist by O of np, where p is some fixed non-singular point. Because we want to have a degree 0 object here. So as has been mentioned in my time talk, the fibers of this map will always be projective spaces. So to be explicit, if you have some element f in J, then the fiber of the Albert-Jacobi map over f is something like all the different ways you can write f as an ideal sheaf, up to some twisting, and then you check if that is in fact the same thing as the projectivization of this vector space here. Okay. So in particular, when n is big enough, you can use Z-duality and Riemann-Roch to show that the dimension of this space is actually independent of which f you choose. And so for n bigger than or equal to 2 times the genus of the curve minus 1, we then have that this Albert-Jacobi map is a projective space function. So in particular, already here you can see that if you're interested in the homology of the Hilbert schemes, you can, for large n, you can get that out of the homology of the Jacobian. Okay, just projective bundle. Let's see if it write down the formula. So what we're heading towards is being able to say something about the homology of C and in terms of the homology of J for values of n which are lower than this range as well. Okay, so there's one last piece of sort of preliminary background material we need, which is the following thing. So this is a statement saying that when C is locally planar, you can somehow smooth out the Hilbert schemes of your curve, and also the compactified Jacobian of your curve, meaning that you can deform your curve in some big family, such that when you get this induces a family of Hilbert schemes, and a family of Jacobians, and then the total space of that will actually be non-singular. So probably easier to see written down. So there exists a deformation family of curves. So C is the central fiber here. Over some smooth face B. And then we write curly C for this family, such that this relative Hilbert scheme and the relative compactified Jacobian these two spaces are non-singular. So this result is due to the extender, and this is due to Antecchi, Ritchie, and Van Straten. So in the so the statement about the Hilbert schemes is more or less comes out of the fact that the Hilbert scheme of a surface, Hilbert scheme of points on a surface is true. So you can, at least locally, you can think of your curve as embedded in some surface, and then if you just take some big enough family of curves inside that surface, then the family of Hilbert schemes naturally maps down to the Hilbert scheme of the surface. So if you just think of C as embedded in the surface and deforming inside the surface, then this thing naturally maps down to the surface, and then you can check that if your family is big enough, these fibers will all be non-singular, and then the total space of Cn will also be non-singular, since we're fibering over a non-singular space. Sorry. And the family, yeah, the base. So big enough is, yeah, it's vague in this context, but yeah, versal is the keyword, yeah. Yes, if you take a versal family, so you don't have to take a versal family, but that is certainly big enough, yes. Right, okay, so that was the background. So now to actually studying the homology of these Hilbert schemes. So we're going to construct a Heisenberg action on these homology spaces. So this is very directly inspired by Nakajima's construction, or Nakajima and Granovsky's construction for Hilbert schemes of the surface. So in a way, what we're going to do here is to get some very much smaller version of that Heisenberg algebra acting on the homologies of Hilbert schemes. And so so the algebra involved, the Heisenberg algebra involved, is much simpler, and the relations you need to check are much simpler. Whereas the new thing is that is the problem of dealing with the fact that C is a singular space, and also to see how you bring the compacted by Jacobian into the picture here. But if you're familiar with this, the Nakajima construction, then this should be fairly, I mean, you'll recognize the structure of this thing anyway. Right, so what we'll do in this case is to define 4 operators. So let me just write down these are called and where they're mapping to and from. So these are pairs of creation and annihilation operators. So there's mu plus point, which goes from homology Cn, and then there's this so it changes the homological degree by a certain amount, which is this, and also takes you up or down in the number of points according as to whether you're looking at mu plus or minus. And then you have mu plus or minus C, which is fairly similar. Right. So let me just first explain so one pair of these operators is fairly easy to describe. The other one is slightly tricky. So let me first do the easy pair, which is mu plus or minus of a point. So these should roughly correspond to adding or removing a fixed point in the following way. So if you just choose, if you just fix a non-singular point P in C, that gives you an inclusion of Cn into Cn plus 1, simply by taking a subscheme and then sending into the subscheme where you've added on P. And if P is already in the supportive set, you just up the multiplicity by 1. And then you can define mu plus the point just as being push forward along this map, and mu minus is the intersection pullback. So this thing sitting inside n plus 1 is actually a Cartier-divisor. So that, in particular, this means you can take a cycle in Cn plus 1 and intersect it and restrict it to C and lowering the homological degree by 2. So that's perfectly. I mean that's easy enough to do. The second pair of operators is more tricky. So by the way, all of this is, so in the surface case you can define all of this in one go, because you're working on the Hilbert scheme, so then intersection theory works because these are non-singular. So the reason you have to work here is because you can't really define things by intersecting classes, at least not obviously. So therefore you have to use these sort of ad hoc constructions. But yeah, so let me say what mu plus minus, mu mu plus of C. So what do we want this to be naively? So suppose you were just looking at the case of a nodal rational curve, and just to take something, let's just look at the one cycle, alpha. That's not Cn. So this one cycle alpha inside the Hilbert scheme of 1 point on C. And then so when we act on this on u plus C, we want to get something in. We want to get a free cycle in the Hilbert scheme of 2 points. And the free cycle we want is the one where 1 point lies on alpha. So this is point 1. And the second point, point 2, is allowed to roam over all of C. So in the smooth case, this is more or less, if C were smooth, this is more or less a reasonable definition. The problem here is it's not obvious what this cycle should be when points 1 and 2 come together at a singular point. So so there's a problem with how to formalize this naive idea for an operator. So what would you do? So the natural thing to try to do if you want to formalize this is to introduce the following state, this flag Hilbert scheme, which is just a set of pairs Z and Z prime. Sitting in the different Hilbert schemes, where Z is contained in Z prime. So you get Z prime by just adding on a point. And then this has, of course, maps down to Cn and Cn plus 1, all these T and Q. And then you could want to formalize this by saying mu plus C equals Q lower star P upper shriek, where you think of P upper shriek as just taking the inverse image of a cycle. But it's not easily done. That's it. So that should correspond to the operation of just adding a point anywhere on C. And I haven't really said what we want mu minus C to be, but you might guess that it's the correspondence which goes the other way. Okay, so this is better. This is more formal, but still there's a problem with these upper shriek maps. There's no. So if C were smooth, we could pull back homology classes easily just by dualizing, pulling back the homology class and dualizing back again. So there's an issue here with defining these upper shriek maps. But we can still do it. And I don't know, I think this is kind of curious because this all comes down to the fact that C is locally planar. So if C is not locally planar, you can't define these. But if it is, you can. And I'll tell you how. So you have this. Remember that you had this family, this deformation family, such that the total space of the Hilbert schemes were smooth. So that gives you the following diagram, Cartesian diagram. you've got the map P, and it sits as the central fiber of this family version of this. Okay, and now we know that this thing is non-singular. So now it's the fact that since this thing is non-singular, you can intersect cycles on it. And that works in this general context. Anytime you have a cyclone or a homology class in the upper right-hand corner and in the lower left-hand corner, you can intersect them over this smooth thing and then get something in the upper left-hand corner. So the refined intersection product. So that means if you start with some alpha, some class with Cn, you can intersect the fundamental class of this curly C n plus 1, and that will give you a class in C n plus 1. And as it turns out, that is the reasonable pullback map you want. So this is the refined intersection product. So it's not hard to write down what this refined intersection product is in terms of more, I don't know, to write that down in other ways, but this is already getting a bit technical, so let me just leave it at that. So that gives you the pullback map P upper shriek, and you can define, of course, Q upper shriek in the same way, and that means you've got access to this other pair of operators as well, U plus or minus C. Okay. So now that we have two pairs of operators, so what can we do with them? What can we say about them? So we start by just introducing some notation. So VC is just a vector space, which is sum of all the homologies of all these Hilbert schemes. Okay, and then the operators, of course, act only of C. So the theorem is, first of all, they satisfy, they are actually operators in a Heisenberg algebra, so they satisfy the appropriate relations. So the operators satisfy commutational relations. So the following relations, minus plus point commuted with mu plus minus C is plus or minus the identity, and all other pairs commute. So from this, you can then write down a natural set of generators of generator space there for the space VC as follows. So you define W just to be the intersection of the kernels of mu minus point with the kernel of mu minus C, and then there's a natural map from W tensor with the polynomial algebra in u plus point and u plus c, going into so anytime you have anytime you have a polynomial expression in these two, since they commute, you can act on an element of W and get something in DC, and then this thing is an isomorphism. So this second part is I mean that's just linear algebra if you know the first part. That's purely formal. And so the third part is to bring in the compacted Jacobian in there, and so the statement is actually then that the space W is naturally isomorphic to the homology of the compacted Jacobian. So so the map HA, the Jacobi map, going from the Hilbert schemes down to the Jacobian. So these induce push-forward maps. So you have the map AJ from Hilbert schemes down to Jacobian, and that gives you the push-forward map from V of C to the homology J, and then that induces an isomorphism between W and the homology of J. So in particular, what you have here is that the homology of Jacobian is isomorphic is naturally isomorphic to W, and W generates the homology of all these Hilbert schemes, and then so then that implicit in this is the fact that you can actually then reconstruct the homologies of the Hilbert schemes from the homology of the Jacobian. So if we just write down explicitly what this says, so this space VC is naturally graded just by n by the different Hilbert schemes. So the nth graded component is just the homology of just the homology of C back to n. And then this grading then restricts to a grading on W. So W is M graded, and then since W is isomorphic to the homology of J, that gives you a grading on the homology of J. So you can write this then as direct sum of in this way, and then if you just unravel what the theorem on previous slide says for an individual, says for just one Hilbert scheme, you get the following corollary, which was previously shown by two pairs of authors, Molik and Jung, and Migliorini and Schender. So they show the following thing, namely that the homology of each Cn is expressible in terms of the following formula. So there's a sum with k of the kth grade P's tensored with the following vector space. Okay, so the q and the q minus 2 just represent the operators mu plus point mu plus c. So this looks, so if you just, well, I could probably, right, so this is then a generalization of that formula, okay? So H even is Q plus Q shifted by 2, and then this thing is the wedge product is the homology of the Jacobian. Right, so I want to say something about say something about grading, which was used in these. Sorry about that. Yeah. So I want to say something about so the grading which occurs in these two papers is different. I mean, they approach this problem from a completely different angle. So let me just say briefly what they do. So they so what they do is they take the same thing, the usual thing almost here. Take this big family, this deformation family. This gives you again a family of Jacobians over your base B, and then if you take the derived push forward of the constant sheaf, then that's down, so F here is taken out to base. So this gives you an element, a constructible complex of sheaves on B. And then this thing has a perverse filtration. Perverse homology filtration. Which you can then restrict to the homology of the Jacobian. So this thing has a filtration, and then that gives a filtration to, so this is I, so that gives a filtration to pull back this complex to the point 0, which is naturally the homology of the Jacobian. So this thing also has a filtration. And then you can choose a splitting, and that gives you a grading instead of a filtration. But then, I mean, so that's something which shows up in this approach, which isn't in the previous two papers. Is the fact that there is a natural splitting of this filtration, which is a minor point. And of course, these two papers do quite a lot more than just prove this corollary. It's a corollary in their paper as well. So what they do is actually to somehow more or less explicitly identify this, or describe this derived push forward of Qk, and then also describe the derived push forward of the constant sheaf on Cn as well, and then just match up the two sides and show that they're equal in the way that the formula requires. anyway, so this was sort of the main motivation for working on this, was to try to, because the statement of the corollary doesn't really use the family in any way, and so somehow using further, you should be able to get the corollary without using the technology of further sheets. So that was sort of the starting point for this, to get rid of that. Okay, so let me just say something about how to prove the theorem. So first, let me just say explain the strategy for proving the commutational relations. So the thing is, these operators are all correspondences. Which means that you can compute their composition as a correspondence. Okay. So you can compute the composition of two operators and get a new correspondence. And then these things can then be studied geometrically and understood. So let me just do the example. Of proving that commutation relation. This commutator is the difference of two compositions, and so the first one is this thing, which corresponds to first going up to this space and then pushing down to C n plus 1, and then intersecting down to Cn again. And then we form the fiber product here, X, and then the composition is then naturally defined by pulling up to X and pushing down to Cn. So if you do the same thing with the other correspondence, the other pair of operators, you naturally end up with so what you end up with is this thing. And then what you can show is that the image of X inside this product is just the image of X inside the product is just the image of the n minus 1 n union the diagonal. So this is just, if you sit down and work out explicitly, just set theoretically, what is this fiber product X, what is its image in Cn plus Cn, what is the image of Cn minus 1, and under this map in this product, you end up with the statement that the image of X yes? Sorry, what was that? Yep. Yes, okay, sorry, I skipped a step. Let me do this properly then. So what you get is, so this composition is first you restrict to Cn minus 1, and then you do the correspondence, which is this thing. So the map on the going down on the left hand side is just a composition of these things. Okay. So the image of x is the image of Cn minus 1 and union the diagonal, and then when you take fundamental, so the fundamental class of x, or the image of x rather, is the fundamental class of Cn minus 1 n plus the class of the diagonal, which means that the operator on the left is the composition on the left is the composition on the right plus the identity. So this is what you would do in the case that C was smooth. So because C is singular, this isn't really a valid argument, but you can modify slightly, but just working in the whole family such that the total space is actually smooth, and then yeah, it's sort of technical, but you can, using this trick of putting C inside a big enough family, inside a big family, so that you get smooth total space, you can actually make this work. And in proving some of these commutation relations, you also have to take care of some I mean, it's not always as clean as this saying that the image of one thing is the union of other images. On the nose, you might have to take care of some bad set of lower dimensions, but you can do that because essentially for the same reason that the computations work out in the Nakajima case. Right. Right. So just to say a couple of words about the third statement here. So we want to show that the object-body push-forward map actually induces an isomorphism from W to the homology of J. And once you have these operators and these commutation relations, it's not really that hard to do it. So that more or less follows from the fact that you have a projective space bundle. So it more or less follows from the fact that when n is big enough, this thing is a projective space bundle. Because first of all, you can then you know the dimensions of the homology of Cn and how they relate to the dimension of the homology of J. So right away you can just compute both and check that the dimension of W is the same thing as the dimension of H over star J. And then apart from that, everything, I mean, since this is a projective space bundle, everything is sufficiently explicit that actually checking the statement that HA, so checking the statement that HA low star from W is injective. It's just an easy computation. yeah, this is easy. Right, so there's one more thing I'd like to say, which is just there's a question of trying to identify this grading in a different way, in a more sort of intrinsic way than actually just saying we have all these operators and we have a map from the space down to the homology of Jacobian, and this infers a grading on the homology of the Jacobian. So one would like to have, or I would like to have, a grading on the Jacobian that you can sort of just see in terms of the Jacobian itself. So we have this n grading. So the homology of J. So switching to homology now. This is a sum of n graded pieces, and so you can split this up into two filtrations. And this filtration is the perverse filtration that was used in the papers of Molecule and Migliorini-Schende. So the question, well, one interesting question is, what is this thing? So there's a conjectural answer in Molik-Schön's paper, which says that let me see. So we write Fn for this piece in a filtration. Okay. Then claim is that F is the finest filtration such that hard Lefschetz holds when you take the associated graded object. So hard Lefschetz holds for this associated graded object with respect to the action of the theta divisor on the Jacobian. So that would be, yeah, that would be a nice, that would, for instance, tell you that you can actually reconstruct the homology of any Hilbert scheme just by knowing the homology of J together with the action of theta on this homology. So no need to introduce these deformation families or privileges or anything. So one thing we can say about this is the last thing I'm going to say, is that this thing is true if when you take the push forward of each Cn, this thing should be equal to c to the power n divided by n factorial. So in the smooth case, this is well known, and as far as I know, it's not known in the singular case or in the nuclear planar case. So if anyone has an idea about how to prove this, I'd be very happy. Right, that's it. Thanks for listening.